speaker is Slađana Radinović from the Spanish Institute of Space Sciences, and she will talk about Alcock-Paczyński test, but not with galaxies, but rather with quality points.
Okay, I'll try not to breathe into the mic too much. So I'm Slađa, and as said, I'll talk about voids mostly. But first, I think for me, in the last couple of years, the most exciting result that I saw was the DESI-BAO constraints on dark energy equation state, which shows that maybe there's some signs that dark energy might be evolving. Super exciting. Now, István has already mentioned the BAO scale, and how it's a bubble. So what DESI people did is used this knowledge that we know the scale, or at least we think we know the scale of BAO, to do an Alcock-Paczyński test. This is a test using the Alcock-Paczyński effect, which is basically this idea that we have to convert the observed positions of things, angles in the sky and redshift, into physical distances. So you can think of the universe using the true cosmology to convert physical distances into what we observe, and they are related with the angular diameter distance for angles perpendicular to the line of sight, and the Hubble distance for things along the line of sight, which gives us redshift. Since we have to convert back, we have to assume some cosmology. These two things depend on the cosmology of the universe, but we don't know the true one, which is why we're doing all of this. So we assume a fiducial cosmology, which is probably different than the true one, which means that these distances that we get are now different than the true physical distances. Luckily, the relationship between the true and the fiducial distances that we get, is they're related with these very simple scaling parameters called the AP parameters, perpendicular and along the line of sight. To show the macroscopic effect of this, on the example of BAO, it's easier if we recast these two parameters into Q, which is isotropic, and epsilon, which gives us sort of the distortion of this shape. So for BAO, we know the scale of the BAO. So if it's different, what we measure is different than what we think we know, we will get some Q that is different than 1. If knowing that BAO should be spherically symmetric, we get something that's distorted. This epsilon is different than 1. And these two will tell us how far we are from the true cosmology. So why am I talking about this? This epsilon, actually, we can also constrain with cosmic voids. And we do this by looking at shapes of voids. So voids are a class of underdense objects. And if we live in an isotropic universe, which we think we do, and we usually assume when we do cosmology, on average, the void shape should be spherically symmetric. In reality, they're all different sizes and different orientation, but if you stack many voids on top, in the end, you will get some sort of a spherically symmetric object. In reality, of course, there are observational effects that will violate the spherical symmetry, but this is a good thing because we're going to use these to get some sort of information about the universe. So the first one is the AP effect, which I just described. However, there's an additional effect, of course, redshift space distortions. So you start with something that's spherically symmetric. You sort of distort it by virtue of not knowing how to get the actual physical distances, but then also you don't know what velocity these tracers that you're using have, so you get an additional distortion because your redshift estimation is wrong because there's an additional peculiar velocity component. I just talked a lot about RSD. I won't be talking more about RSD because it's not that important for this talk, but it is important in the model that I will be using later. So for the shapes of voids, the way we measure them we used the void galaxy cross correlation function, which basically describes the distribution of galaxies around voids. And it will help us measure how spherical voids really are. And you see on the left, yes, on the left is the real space cross-correlation function, which means the real space distribution of galaxies around voids. And you see that it looks by eye spherically symmetric. And then on the right, you see the redshift space one. So now we have redshift space distortions. You see that the shape is distorted. What we're actually going to be using is a decomposed version of this into multipoles. So the monopole shows you the sort of shape of the void. You see it's underdense in the center and goes off to 0, the average density of the universe. And the quadrupole, the more important one in this talk, which shows you whether something has RSD or AP distortions. And so here, it's very much not 0. And it's showing this redshift space distortion. Just a disclaimer, these monopoles are not actually from this cross-correlation function. I couldn't get the data to get this plot again, so don't try to compare. The general shape is the same. So the actual model that I'll be using here is just a mapping from real to redshift space for the cross-correlation function. And the important part is that the AP effect gets put in here at the end. Basically, you put in your RSD, and then in the end, you perturb the distances along and perpendicular to the, not perturb, sorry. You add in distortions along and perpendicular to the line of sight to get your AP distortions. So what we basically do, just ignore the simulation part. I don't think I have time to talk about that, and it's not that important. You get some true cosmology, you put in RSD, and then you put in AP, and this is basically what you measure in observation, some sort of RSD distorted, AP shifted, redshift space cross-correlation function. Cool. Now, everything that I've talked has made a very crucial assumption. And this is that all of this AP stuff works for galaxies. This has been tested, and it's true. They really do move with these Q parallel and Q perpendicular parameters that I've mentioned. However, does this work for voids? We're pretty far into the talk to be asking this question now, and I think because I'm asking it, you already know the answer. But let's see. So we tested this assumption. First, we looked at 2 cases. First, we said, let's make the assumption true by construction to make sure that the model actually works if the assumption is true. And then we did that by taking simulations, doing void finding, and then shifting both galaxies and voids by hand, so that we know that the shifts happen the way we say that they happen. Then we did like a realistic true test, where we took the galaxies, we shifted the galaxies, and then did void finding on that shifted catalog, which is what would happen realistically if you have observations. So in the first case, if you take something without any AP, you get this quadrupole consistent with 0. So these are cross-correlation quadrupoles. I said if things are spherically symmetric, it should be consistent with 0, and it really is. This is the real space. Then we put this into the model. We add in RSD and we add in AP, and we get this gray line, which is the redshift space, the modeled redshift space quadrupole. Cool. Now we take that those catalogs from the first phase, the stuff that was shifted by hand. We measure the real space quadrupole. Okay, it's not spherically symmetric anymore. And we measure the redshift space, and what do you know? The theory describes it perfectly, almost. Excellent, so the theory works if the assumption is true. Now we do the actual test, and it looks so much different. We see here that void finding on this distorted catalog has somehow washed away some of the signal, and the quadrupole is much smaller than it should be, than we expect. And when you actually compare it to the theory, it looks way different. That's not very good. So we did this for 4 different void finders, and we did MCMC chains for many different values of epsilon. So we assumed different cosmologies, and we took all of these simulations and shifted them by different amounts. And what you want is this black diagonal line. You want to recover what you put in. You want to make sure that you're actually getting the epsilon that you should be getting. In the yellow case, where we moved things by hand, of course, we saw that it works, and we really do get, we recover the values that we should be recovering. But in the red case, in the realistic case, there is a significant bias for all of the void finders. Now, the lucky thing is here that this bias seems dependent on the epsilon itself. So the further you are from the true cosmology, by the way, epsilon equals 1 means you're at the true, you've guessed the true cosmology, this is the one you want to get. If you're further from epsilon equals 1, the worse your bias is. We can use this knowledge to then try to iteratively arrive at the true cosmology. So you assume your cosmology, you get some sort of epsilon that's different than 1, and you say, fine, my next guess is whatever cosmology I get from that epsilon. And you do this until you converge here. The vertical line is omega m of the actual simulations. We've also assumed here a flat lambda CDM. So we iteratively arrive to the correct value for some of the void finders. The spherical void finder, for example, seems to be working terribly. Don't ask me why. Our conclusion is don't use it for this. We'll try to figure out why, but in any case, there are many other options to choose from if you're going to be doing void galaxy cross correlation function. So in conclusion, voids are an excellent way to do an A/B test and get constraints on dark energy. They can sometimes work better than galaxy clustering, or don't work better. Get better statistical significance, which are 2 different things. They're definitely a good complementary probe to galaxy clustering, like video. And they, as the word cloud at the beginning showed, they're getting more and more popular. So get on the wagon while it's still fresh. However, make sure you test all of your void finding algorithms. They are very sensitive to the status of your tracer field. Any sort of systematic, any sort of distortions will propagate through your void finding. So test your algorithm, and also don't assume that if one of them works, the other will work. Different algorithms all do different things. So you have to test yours specifically, which is kind of a big.
Questions? Yeah, okay.
Thanks. But the third bullet points, the sensitivity to basic cathode, have you tried to do it on different subsets of the data? Red galaxies, blue galaxies?
No, so we didn't do like a galaxy separation thing. The only sort of subsetting that we do is take away small voids. So nothing on the galaxy catalog, but on the void catalog, there's a cut. I don't expect things will be much different, because it's really not about what your tracer is. In a sense, if this is not a problem, it means the tracer is not as distorted. In which case, you're not really getting the AP information you need, which is why you're doing all this. You want a strong AP signal so that you can constrain it, but that will make your void finder work worse.
Perhaps it's a naive question because it's not my field, but You understand that you assume that the voids intrinsically are spherical. What if it is not true? I mean, why should it be true?
That's an excellent question. So if the universe is isotropic, this has to be true. Because you cannot have, on average, so if you're stacking many of them, there can't be a preferred direction. So they need to be isotropic. If the universe is not isotropic, you do something else. For the stuff we find, at least, if things are in real space, you really do get a zero quadrupole. So they do seem to be statistically isotropic in simulations.
Okay, thank you.
Yeah, but further on, and surely just selection effects could produce, for example, a radial alignment.
Yeah, so
and in your talk, it wasn't clear to me sometimes whether you were talking about voids found in real space, which of course we cannot do in actual data, or in redshift space. But in redshift space, I think you could make a case that things ought to be radially aligned. And that's surely a problem. This analysis.
It really is. So the first thing is just I want to make actually saying that they're spherically symmetric is not correct. What I mean by that is to say that the quadrupole is zero. So some higher order quadrupole could be non-zero. Then there is the question of redshift space voids, which indeed there has been studies done where redshift space finding in a redshift space catalog will give you selection effects, and this model that I was showing will not work as well. What we do when we actually deal with data is reconstruct to get the, let's say, pseudo real space positions, reconstructed real space, and have some sort of almost isotropic catalog. On top of that, there could be some sort of other purely observational systematic, just based on how you're observing, that could induce a quadrupole. And that you could mitigate by using, often in this, people assume that it's spherically isotropic and they just use the monopole. For the real space, they just use the monopole. You should not do that. You should put in the quadrupole, and this will help. For example, if the reconstruction that I mentioned isn't working as well, this might be captured in the quadrupole, and then you propagate this through to the final. I don't know if I explained that well. Maybe later we can talk.
Okay, very last question, Alexa.
So, Doreen van Wyker 2 decades ago simulated the topology of the universe with a Voronoi form, where essentially the maxima of the gravitational potential roughly corresponded to the vortices of the Voronoi. So in this model, the voids will never be perfect spheres, but they would be sort of a polyhedral approximation. So it would be worthwhile to do something like, take the gravitational potential with these Lambda-Cilian power spectrum, take the maximum of the potential, generate a Voronoi form, and try to see that actually what is the shape distribution in this space.
But this will induce higher order multipoles, and so far we haven't seen significant, at least within the error bars that we've looked at, because this is all observationally oriented. We haven't seen anything that's a big signal enough that will be observable.
Well, it would cause a larger variance. So
That's true, yeah.
You still would expect to know that all these things, when you average out, they would be actually spherical, but it is more than this is sort of a higher order perturbation, but nevertheless increase the variance for all higher order multiples.
It could,
including the quadrupole.
Yeah.
Okay, thank you, Steng. And